Last time we have seen how the SIFT algorithm is working. Today we are diving into SOF, which is speeded up robust feature. So it's a super smart technique that helps a computer to find and also recognize important, let's say, part of the images, like what we have, what we recognize faces. So SOF is we will see it's incredible fast and robust. It's not like, let's see, it's not more accurate than soft, but it's very fast and also robust with changes like in rotation and also resizing. And one hint to this, it's patent. So if you would like to use it a commercial in your product, so you have to buy this license, or there's also other alternative, for instance, ORP. We will go through this and we will see how it's working. But you can see from this here stuff, it's getting the input, calculating the integral image computation, then scaling up, and there's a difference between SIFT and SIF. The SIFT is resizing the images, and the soft is resizing the filter. We will see in a moment, and also finding the interesting point, and after the interesting point, we will try to calculate the descriptor of this interesting point, and we will use, for instance, for matching. We will see in a moment. So before diving into this first, let's see the basic stuff. So what are the local features? The local features are the distinctive part of the image that can be, let's see, founded in a different views of the same scene. And the interesting point is are the specific and stable locations where these features are found. And the feature descriptor are a unique, let's see, as a fingerprint of these points, allowing computer to match them across different images. So you have local features, you have key points, and from the key points we will try to extract, let's see, descriptor, or let's see, features. And this is the image gradient we have already seen in the edge detection, corner detection, how to find this gradient, and also the key point descriptor. We have seen it in the SIFT, but we will do this also in this heat. So what is the why is SAF is let's see, is fast. So the secret here is integral image. Imagine a pre-calculated table where each point sum up all the pixels in the left and also above. So I will just give you one example here. And this, let's see, this magic allow to calculate the sum of any rectangle after calculating the integral of the using the four symbol with this magic, let's see, formula. So how to calculate the image integral? Let's see. So let's starting with this pixel here. So there's the integral. You can see here the integral image is at each point. The integral image is stored the sum of all pixels above and the left. So you can see here there is no left, there is no above. So the sum is 1. So let's start with let's see, try with this 3, and 3, the left is 2 and above is 2, also including itself. So and but 1 is also above and left. So you can see when you select, for instance, this pixel here, you can make it like this and sum all of these pixels. So for the pixel 3 will be 3 plus 2 plus 2 plus 1. And for the 5, I will say 5 plus 4 plus 3, and all these pixels here. You can see this, the whole rectangle here. And for the 2, it means sum all of these up, all the pixels, the last one here. So this is the integral images calculation. So for why we said why we have why it's fast, we can see this is the magic. So you can see if we calculated the integral, we will see, for instance, this pixels here. It's B A B C D. It's somehow four C. It's A B C D. They see it's wrong. Now we can see find the the value of this pixels here. You can see D minus B minus C plus A. So this is the integral image. Now, indeed, it's used as Hessian matrix and box filter. To find the interesting point, SAF use Hessian matrix to detect the areas of rapid uh, uh, intensity changes, and it has three different filters, and each filter has different values, and we will for instance selecting any let's see region or 3 by 3 pixels and try to convolute this. So we will try to find dxx, which is the changes in the horizontally, dxx horizontal and the vertical, the y is vertical, and this one here is diagonal, and each filter has specific values. Let me just show you the values. So you can see here, this is dxx, the horizontal second derivative. This is the filter values, and this is dyyy and dxy. So you have, for instance, if we have this image, 3 by 3 image, we will try to find three different values from each filter. I mean, three different values from all filters. One value for this, one value for this, and one value for this. For instance, you can see here, this is the image. This is the image and this is the filter. We have to multiply. It's a convolution. We have already discussed this several times. And you can see this is the value, and this is the second result of the second filter, and this is the last one of the second filter. Now the Hessian determination, it has to be calculated with this determination, with this equation here. You can see dxx times dyyy minus 0.9 times dxy. So you can see it's a matrix dx, then dy here, and dxy. Okay, it's hopefully this is clear. Otherwise, let me just show you what I mean by this. So it's like Hessian determination. You can see dxx, dyx, dyyy, dxy, and dxy. So calculating the determination, it will be like this. And after getting this dxx, dyyy, it's already calculated from here. Now we have to see if it's greater than a specific threshold. Let's see, we have said 400 the threshold. Now this is considered as an interesting point. Sorry. Okay, so we have already seen this, how they calculated. This is the filters. And now let's see the scale up scale space representation. So you can see here object are at different sizes. So self need to find features at multiple scales. It's like it's unlike the traditional method. Let's see, SIFT. In the SIFT, which is trying to shrink the images into several octaves. We have seen. Please, if you are not familiar with this, please have a look in the previous video. And the surf here, it keeps the original image. You can see the original image is exactly the same, and but just because it's far away. But this is, you can see the filter. For example, this is the filter, the second one, the third one, and etc. So every time they increase the filter size, and you can see here they're starting with 9 by 9 filter, and increasingly it's 15 by 15, 21 by 21, and etc. So but the image size, it's still the same. So now after getting the interesting point, after having the interesting point, so now we need to use the orientation assignment. So it's similar to the surf and also in edge detection, how to define the orientation. But let's see here we have they divided this into six orientation sectors. So what does that mean? If you see from minus 30 to 30 degrees, it's for instance, this is 1, 2, 3, 4, 5, 6. So this is the six vectors, and each now they will calculate the orientation of each gradient with this here. For instance, they have from minus 30 to 30, they have there are three point, let's see, point 54. And after finding the let's see, dominant orientation is 25, they will now try to let's see oops. So now they will try to find the descriptor of this interesting point. So once we have this, let's say, oriented key points, we create its features. Let's see its finger, sorry, its fingerprint. So it's divided the image into square region. Let's see, square divide into 4 by 4 regions. Assume that this image here, sorry, this image will be only, as example, 20 by 20. Now, if we see 4 by 4, it will be 20 by 20. It will be 5 by 5 sub-regions, right? So it's 20 divide 4. It will be 5 times 5. It will be dividing the image into 5, 5, 5, 5, 5, 5, 5, 5. And how many of these? It will be 4, 4 times 4 times 4. I will tell you why we get this 4. So now for each subregion, we will try to define the gradient in each direction, x, y, for instance, this x and y, and this is the descriptor of this let's see region here, and we have dx, summation of the dx, which is the gradient in x direction and the gradient in y direction, and the summation of the absolute value in x direction and the absolute value of y direction. So now here we have four values here. Then this region here is represented with by four values. Also this one here will be 4, 4, 4. Now how many dimensions? We have 64 descriptor factors for each for all this let's see points. Now why? Because 1, 2, 3, 4 times 1, 2, 3, 4 is 4 by 4, and each one is represented by 4. It will be 60 64. And if you see here now, each feature or its region is represented by 64, right? And now if you would like to have, let's see, comparison between two images, you will calculate the distance from this feature A, for example, to the feature B, to the feature C, for the other images. This is just as example. Now, what are the applications of this, and why it's meta, and why not using, let's see, surf? So as we have discussed in the beginning, surf speed and robust make it invaluable. It's used in object recognition, identify specific, let's see, items, image stitching, and also 3D reconstruction. So one again, the surf it's not allowed to use in the industrial project, or let's say commercial project. Other than that, you have to use license or use another free stuff. And this is a comparison between several methods. For example, this is the serve. This is the last one we have discussed, sift, and this is might be the next one. This is one is free. These are patent. So as we said, you have to have a license if you are using in a commercial projects. So this is the summary of this, and its speed. Why it's speed? It uses integral images and box filters. Detection is based on the determination of Hessian matrices, and invariance. Even if the images are rotated or scaled, it's it will be detecting the matching, and the description of each key points is 64, not 28, 128. It's 64. This is the shift features, and it's not, I would say it's not smart as the shift, but it's really fast and ticked the most important features for you. I think that's it for today, and if you have any question, just drop the question in the comment below. I will answer it definitely. Thanks for watching and see you next time.